Okay, good morning. So today we're going to start with a conservation of energy problem where somebody is running for their lives. They're going, help me, and they're going to grab onto this rope swing and they're going to swing as high as they can. They're going to swing up a height of h. And I just want to point out that h refers to the additional height that the rope will swing from its resting position. It doesn't factor in anything down here. It's really just this additional height right here. So our question is going to be solving for how high does the person swing, and then what angle. Oh, okay, my wife's got a chiropractor appointment. Okay, so apparently I should have shut off notifications. But how high do they swing, and at what angle will the rope swing make? So, I can see somebody's coming into class late. Wes, thank you for coming in today late. Just please have a seat and don't draw attention to your. Wes, be quiet. Wes, just stop. Stop, Wes. Just sit down. Okay. Yeah, you. Okay, sit down. Okay. So anyways, back to what we're doing. Let's give this person a velocity, an initial velocity of, let's just say, 5 meters per second. And let's give this rope an initial length of, let's say it's a 3 meter long rope. So again, the questions are, what will the theta be? And how high will they swing up? So the first thing we always have to do on these types of energy questions is ask yourself, what kind of energy do you have before and what kind of energy do you have after? At the beginning, all you have is kinetic energy. And at the end, when you've stopped swinging, you kind of swung up to your maximum height here, all you have is potential energy. So the energy before always has to equal the energy after, which means that all your kinetic energy is going to be transformed into potential energy, which means that you have 1/2 mv squared. That's all going to be turned into mgh. All right, so you can see that we can, this is how we're going to get the h right away. Theta is maybe not so obvious, but we'll get to that in a moment. We'll get to that once we get h. So notice that I never gave you a mass of this person. Well, notice it didn't even matter if I did, because the masses will go away anyway. And it's interesting in physics that a lot of times that the mass of an object is irrelevant to what happens to it. So in this case, it doesn't matter what mass I gave you, the masses would cancel. And so 1/2 v squared will be equal to gh, which means that v squared all over 2g will get you the height that this person will swing. And again, this height refers to the additional height of the rope swing. So now this is going to be, what is that, 5 squared all over 2 times 9.8. And I got my handy-dandy calculator that has a couple pixels broken in it because it's technically not mine. I was a senior student who left it behind, and so I inherited it, because who wants to pay for a calculator if they don't have to? 1.28 meters. Okay, so 1.28 meters high. So 1.28 meters high is how high they're going to swing. Now, the more interesting question is, what angle will the rope swing make? So this is going to be sort of a geometry type question. So I'm just going to do this in pink. Here we have the rope swing initially, and then here we have a rope swing here. And this height we have calculated to be 1.28 meters. The rope swing was initially, the entire rope swing was 3 meters, and we're trying to get this angle here. So this is very important geometry that you definitely don't want to blank out on or just drift off on. Ellie, do you have a question? No? Well, then pay attention, Ellie. Come on. Pull it together. All right. Sorry, Ellie was drifting off there for a moment. So we're trying to get theta. So let's make a triangle this way. We're going to make a right triangle this way, where if this whole side on the left-hand side here is 3, that means that this part down here is going to be 3 minus 1.28. And this whole top part, I'm sorry, apologies. This part right here is 1.28. And this part up here is going to be 3 minus 1.28. Right, because if the whole thing is 3 and then this part from here to here is 1.28, that just makes sense. this whole side, remember the whole rope itself is 3, so the hypotenuse is 3. So now if you, I'm going to do this a little bit thicker so you can see, we're really dealing with this triangle here, where one of the sides is 3, this side is 1.72, and we're trying to get theta. Now, the 1.72 is the adjacent side, so it looks like cosine of theta is equal to 1.72 all over 3, which means that if you want to get the actual theta, take the inverse cosine. So we're going to go inverse cosine, make sure I'm in degrees, 1.72 divided by 3, 55.0. This is where the dead pixel is. So it looks like I'm just gonna say 50. I'm just gonna say 55 degrees because I can't read that pixel. So 55 degrees. Okay, so the theta is 55 degrees up. So this, I'm just going to do this, I'm going to circle this a little bit in pink here. This geometry right here is very, very important for this unit to know how to construct this triangle and how to calculate the angle. That is super, super important. And then just in general, it is very important to ask yourself, what kind of energy do you have before? What kind of energy do you have after? And then put in your equations. So far, we haven't lost any energy due to friction or anything like that, which will lead into your notes today, which is the work done on a system. And remember, work will be a transfer of energy or a loss or gain or a loss or gain of energy. So make sure you're focused on today's notes because it does get a little bit more complicated starting today. Because in this problem, there is no loss of energy. In future problems, there might be.